Before 1995, every astronomer on the planet assumed gas giants had to form far from their stars. Jupiter's out there, Saturn's out there. It made perfect sense. Then two guys in Switzerland pointed a spectrograph at a quiet sun-like star and broke everything. So today we're covering every major type of exoplanet and how we actually find them. Starting with the planets that rewrote the textbooks overnight, hot Jupiters. In October 1995, Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, and the entire field of planetary science had a collective meltdown. This was a gas giant roughly half the mass of Jupiter, orbiting its star every 4.2 days. 4 days. For context, Mercury takes 88 days to orbit our sun, and Mercury is basically sitting in the sun's lap. 51 Pegasi b made Mercury look distant. Surface temperatures hit around 1,000 degrees Celsius, and nobody had a model that could explain how a planet that massive ended up that close. It simply was not supposed to exist, but it did, and it wasn't alone. Hot Jupiters typically have orbital periods of 1 to 10 Earth days with masses ranging from a fraction of Jupiter's up to several Jupiter masses. Most are tidally locked, one face permanently staring into its star, the other facing the void forever. They're actually pretty rare, showing up around roughly 1% of sun-like stars. Many appear to be spiraling inward over cosmic time, slowly consumed by their host stars. A dying breed, and we just happened to catch them. Now, if you want to see this concept pushed to its absolute limit, meet KELT 9b. Dayside temperature of around 4,600 Kelvin. That's hotter than a lot of stars. It's so hot that hydrogen molecules on the dayside are literally ripped apart into individual atoms. Those atoms drift to the cooler night side, reform into molecules, then get carried back to be destroyed again. A perpetual cycle of molecular destruction happening constantly, forever. I don't know what to tell you, but if hot Jupiters sound extreme, wait until you hear about the planets that shouldn't exist at all. Super Earths. Here's something that should bother you more than it does. The most common type of planet in the entire galaxy doesn't exist in our solar system, not even close. We skipped it entirely. We've got rocky planets, we've got gas giants, and we've got absolutely nothing in between. The universe apparently did not get that memo. Super Earths are planets between about 1.2 and 2 times Earth's radius, with masses up to around 10 times what Earth weighs, and they are everywhere. A huge proportion of all exoplanets discovered by the Kepler mission fall into the Super Earth or sub-Neptune size range. The most common type of planet in the galaxy is one we've never seen up close, never stood on, and don't even have a local example of, which is, not ideal for understanding them. And the compositions are all over the place. Some super Earths are bone-dry rocky worlds with very little volatile content, basically oversized versions of Earth with zero water to speak of. Others could carry significant fractions of water or ice by mass, making them potential water worlds. Some models suggest a meaningful percentage of rocky exoplanets in the right size range could harbor deep global oceans, with surface temperatures potentially reaching hundreds of degrees Celsius. So picture an ocean hundreds of kilometers deep, hot enough to melt lead at the surface, with pressure so extreme that the water at the bottom compresses into exotic ice phases that don't exist naturally anywhere on Earth. Not exactly a beach vacation. Then there's Kepler 452b, confirmed in 2015. It's about 60% larger than Earth and was the first near-Earth-sized planet found orbiting in the habitable zone of a star similar to our sun. The press called it Earth's older cousin. Whether it's rocky, whether it has water, whether it has an atmosphere at all, nobody knows yet. It's a mystery box sitting about 1,800 light years away, and we literally cannot open it with current technology. Every super Earth is like that. We know they're there. We know they're common. We know almost nothing else. But if super Earths are the mystery box, then mini Neptunes are the ones actively shapeshifting while you try to figure them out. Mini Neptunes. Remember those super Earths we just talked about? Some of them might be imposters. Planets that look rocky now but used to be something completely different. Welcome to mini Neptunes. Planets with radii between 1.7 and 3.9 times Earth's, wrapped in thick hydrogen-helium atmospheres. They're bigger than super Earth, smaller than Neptune, and they don't exist anywhere in our solar system. 0 examples, not one, which makes them one of the most alien categories of planet we've ever found. But here's where it gets genuinely unsettling. There's a strange gap in the data between 1.5 and 2. Earth radii, planets basically vanish. Astronomers call it the Radius Valley, and for years nobody could explain why so few planets existed in that size range. Turns out it's not a gap. It's a graveyard. Mini Neptunes that orbit too close to their stars are getting their atmospheres ripped away by intense stellar radiation, a process called photoevaporation, just hemorrhaging hydrogen and helium into space like a balloon with a hole in it. Except the balloon is an entire planet, and the hole is its star trying to kill it. And this isn't theoretical. Astronomers have directly actually observed atmospheric escape happening in real time, catching mini Neptunes in the act of losing their gas envelopes. Which means some of the super Earths we cataloged in the last section might not be super Earths at all. They might be the stripped, naked cores of former mini Neptunes. Planets that got skinned alive by their own stars and now just look rocky because there's nothing left on the outside, which is, not ideal. The scale of this is staggering. The Nancy Grace Roman Space Telescope is expected to discover thousands of new exoplanets through gravitational microlensing when it launches, and a significant chunk of those will likely be in the mini Neptune and gas giant range. Thousands of new worlds, many of them potentially mid-transformation, caught somewhere between what they were and what they're becoming. But if you think planets losing their atmospheres is dramatic, wait until we talk about the planets that are genuinely Earth-sized and sitting in habitable zones. Because that's where things get personal. Earth-sized terrestrial planets. This is the one. This is the category everyone actually cares about when they hear the word exoplanet. Rocky worlds between half Earth size and twice its radius, made of rock, silicate, water, maybe carbon. The category Earth itself belongs to. And the crown jewel of this entire category, the system that made every astronomer on the planet lose their collective minds, is TRAPPIST-1. About 41 light years away, one small, ultra-cool red dwarf star, 7 Earth-sized planets orbiting it, 3 of them sitting directly in the habitable zone. The first planets were announced in 2016, with the full 7-planet system revealed in 2017. And since then, every major telescope we have has been pointed at this system like it owes us money. Spitzer, Kepler, Hubble, James Webb, all of them, all staring at the same 7 rocks trying to figure out if any of them could support life. And here's where the data gets genuinely dramatic. Studies suggest the inner planets, the ones closest to the star like Bi and C, likely lost massive amounts of water over the system's roughly 7.6 billion year lifetime. Potentially many Earth oceans worth just boiled off into space by stellar radiation. Some of these worlds may have once been habitable and simply lost it, which is, not ideal. The outer habitable zone planets, E, F, and G, are the ones scientists are most hopeful about for retaining water. Actual liquid water potential on worlds that aren't Earth. Now, before you start packing your bags, there's a reality check. Early estimates suggested that 20 to 50% of sun-like stars in the galaxy could host small rocky planets in their habitable zones. That number felt incredible. More refined analysis has narrowed the range considerably depending on the type of star and the criteria used. Still billions of potential candidates given the scale of the galaxy, but the picture is a lot more complicated than the Earth-like planets everywhere narrative that dominated headlines for years. There's also the tidal locking problem. All 7 TRAPPIST-1 planets are likely tidally locked, meaning one side permanently faces the star while the other sits in eternal darkness. Sounds uninhabitable. But some climate models suggest that the Terminator line, that narrow strip between permanent day and permanent night, could maintain stable temperatures. A thin ring of potentially livable conditions wrapped around an otherwise hostile world. It's hope. Genuine, evidence-based hope. Just tempered with a lot of, but actually from the data. And speaking of worlds that don't play by the rules, let's talk about the planets that don't even have a star to orbit. Rogue planets. Right now, as you're watching this, billions of planets are drifting through the Milky Way in complete darkness. No star. No orbit. No system. Just cold, silent worlds tumbling through interstellar space with zero destination and zero purpose. They're called rogue planets, and the galaxy might contain more of them than it does stars. Let that sink in for a second. For every single star you see in the night sky, there could be multiple invisible worlds floating in the void between them. And honestly, we don't even know if that number is right. Estimates for the rogue planet population vary so wildly, it's almost embarrassing. Some models suggest about 2 Jupiter mass rogues per star. Others push that number dramatically higher when you include smaller Earth mass objects. The gap between those estimates is so enormous it basically translates to, we have no idea, but it's a lot. Which is, not ideal for a field that prides itself on precision. But here's where it gets genuinely unsettling. In 2020, astronomers detected one of the smallest rogue planet candidates ever through gravitational microlensing, basically catching its gravity bending the light of a background star as it passed in front. This thing, it had a mass potentially comparable to Earth's, which strongly suggests it wasn't born alone. A planet that small almost certainly formed inside a multi-planet system, got into a gravitational argument with its siblings, and lost. Ejected into the void permanently. Imagine being a whole planet and just getting kicked out of your solar system like a roommate who didn't pay rent. But the real line-blurring discoveries come from objects sitting right at the boundary between planets and brown dwarfs. Some rogue worlds have been found with surprisingly powerful magnetic fields and even radio emissions, phenomena that scientists previously associated only with stars. So now we have planet-mass objects generating magnetic activity like stars, drifting through space completely untethered. The boundary between planet and failed star just got very blurry very fast. NASA's upcoming Nancy Grace Roman Space Telescope is expected to detect hundreds of rogue planets through microlensing surveys, which should finally give us real data instead of wildly divergent guesses. And before you ask the obvious question, yes, a rogue planet could theoretically wander into our solar system. The odds of a close encounter happening anytime soon are astronomically small. So you can sleep tonight, probably, but if dark worlds drifting through the void creep you out, wait until you hear about how we actually find all these planets in the first place. Radial velocity method. Remember 51 Pegasi b, the hot Jupiter that broke everyone's brain in 1995? We already know what it is. Now let's talk about how two guys in Switzerland actually found it, because the method they used is still one of the most important tools in exoplanet science. Here's the basic idea. A planet doesn't just orbit a star, it also pulls on that star. Every planet exerts gravitational force on its host, which means the star isn't sitting perfectly still. It wobbles back and forth toward us and away from us as the planet swings around it. That wobble changes the color of the star's light. When the star moves toward Earth, its light shifts slightly blue. When it moves away, slightly red. This is called a Doppler shift, and it's the exact same reason an ambulance siren changes pitch as it drives past you. Michel Mayor and Didier Queloz pointed the Elodie spectrograph at 51 Pegasi and detected a stellar wobble of about 57 meters per second. That's roughly the speed of a falling object, not a rocket, not a comet, a thing you dropped off a building. From that tiny signal, they confirmed the first exoplanet ever found around a sun-like star. They won the Nobel Prize for it in 2019, which is, not a bad career outcome. The method is particularly devastating at finding hot Jupiters. Massive planet, tight orbit, big gravitational tug, pronounced wobble. To date, radial velocity has confirmed over 1,000 exoplanets, and one instrument in particular, HARPS, has been responsible for discovering the bulk of known low-mass exoplanets, one instrument dominating an entire mass range. That's absurd. Modern spectrographs like Espresso can now detect velocity variations as small as 10 centimeters per second. We're measuring a star hundreds of light years away, moving at the speed of a toddler wandering toward a kitchen cabinet. I don't know what to tell you, but here's where it gets complicated. Radial velocity can only measure minimum planet mass, not actual mass, because you don't know the inclination of the planet's orbit relative to our line of sight. If the orbit is edge-on, the mass estimate is accurate. If it's tilted, the real planet could be significantly heavier, which means some confirmed planets might actually be brown dwarfs masquerading as gas giants. So the technique that literally launched exoplanet discovery, that earned a Nobel Prize that is confirmed over 1,000 worlds, still can't tell you the true mass of what it found. Turns out, no detection method is perfect. But if you think the wobble approach has limitations, wait until you see what happens when a planet walks directly in front of its star. Transit method. Here's the thing about finding exoplanets. You can watch stars wobble all day, but if you want sheer numbers, you need a different approach. You need to watch a star blink. The transit method works on a beautifully simple principle. When a planet passes between its star and Earth, the star gets slightly dimmer. For an Earth-sized planet, the brightness drop is a fraction of a percent, basically nothing. But with the right instruments staring at the right patch of sky for long enough, that tiny flicker tells you everything. Planet's there. And you know exactly how big it is based on how much light it blocked. Enter Kepler. NASA launched the Kepler Space Telescope in 2009 with one job: stare at 150,000 stars and wait for something to cross in front of them. By the time it retired in 2018, Kepler had confirmed over 2,700 exoplanets, one single mission. Over 2,700 worlds that nobody knew existed. Most productive planet hunting instrument in human history, and it's not particularly close. But NASA wasn't done. In 2018, they launched TESS, which surveys nearly the entire sky, targeting bright nearby stars close enough that other telescopes could follow up and study their atmospheres. Through 2025, TESS has identified thousands of planet candidates. Not all confirmed yet, but the pipeline is enormous. Between Kepler and TESS, the transit method has produced more confirmed planets than any other detection technique. And transits give you two things no other method can match simultaneously: the planet's size, and through transit spectroscopy, Firstly, actual data about its atmosphere. Light filters through the planet's atmosphere during a transit, and chemical fingerprints show up in the spectrum. That's how you figure out if a world has water vapor, methane, or carbon dioxide without ever visiting it. Now here's the honest caveat. The transit method only works when a planet's orbit is nearly edge-on from our perspective. If the orbital plane is tilted even slightly, we never see it. This creates a massive geometric bias. Close-in planets with short orbits are far more likely to align correctly, which means the transit method overwhelmingly finds hot, tightly orbiting worlds and almost completely misses solar system-like architectures. The sample we have is real, but it's skewed. We're seeing the universe through a very specific keyhole, but transits and wobbles aren't the only way to find planets. There's one more method that sounds completely impossible until you realize it actually works, and it involves bending the fabric of space-time itself. Direct imaging. Every other method on this list detects planets indirectly: a wobble, a dip, a bend in light. Direct imaging is exactly what it sounds like. You point a telescope at a star and try to photograph the planet next to it. Simple concept, nearly impossible execution. A star is anywhere from 1 million to 10 billion times brighter than the planet orbiting it. Imagine trying to spot a single firefly hovering next to a lighthouse from 1,000 miles away. That's basically what astronomers are attempting every time they try this method. Because of that absurd difficulty, direct imaging has only confirmed around 70 exoplanets. The transit method has over 4,000. Radial velocity has over 1,000. Direct imaging has 70, which is, not ideal, but here's the thing. Those 70 include some of the most important discoveries in the entire field. The current limitation is you can really only photograph enormous young super Jupiters less than a few 100 million years old. Young gas giants still glow with leftover formation heat, radiating infrared light like cosmic space heaters, making them just barely detectable against the blinding glare of their star. Older planets cool down and essentially vanish into the noise. The HR 8799 system changed the game. Astronomers directly photographed 4 massive gas giants there, about 130 light years away. Actual pictures of alien worlds. And with spectroscopic follow-up, scientists detected water and carbon monoxide in their atmospheres. That's not a wobble on a graph. That's a chemical fingerprint pulled from a photograph of an alien world. NASA's Roman Space Telescope is pushing things further with a dedicated coronagraph designed to test contrast ratios approaching 10 to the -9 in visible light. If it works, it could pave the way toward imaging Jupiter-sized planets around nearby sun-like stars. Cold, ancient worlds that have never been seen directly before. Beyond Roman, scientists are already debating the next step. Some back coronagraph technology that blocks starlight internally. Others argue for star shade designs, giant flower-shaped structures deployed tens of thousands of kilometers ahead of the telescope. Both camps are chasing that 10 to the -10 contrast threshold, because that's the number you need to photograph an Earth-like planet, not a glowing infant gas giant. An actual rocky world like ours. Between every method we've covered today, humanity has confirmed over 5,700 exoplanets. 30 years ago, we knew of 0. The next decade will multiply that number dramatically, and direct imaging will be the method that finally shows us what those worlds look like, not as data points, as photographs. If you enjoyed this video and want to see more, click the video on the screen now.